Good morning, everyone. Welcome to the Smart Water Grid International Conference 2021. I'm Dong Jang from Incheon National University. We are so pleased to see all of you attending this year's conference. This session's title is the Korea EU Educational Cooperation Program, and subtitle is the Hydration. There are 5 speakers, and they will present their first program in the world. And I hope this session is very nice to all of us, and hope to finish well. The first presenter is the Victor Boni from Polytechnic Sofia. The title is the model analysis for mitigation of the flood in river and urban area using canals and irrigation.
Hi everyone, my name is Victor Berni and I am a French student from Polytech Engineering School. In summer 2021, I had the pleasure to work on a Hydration project with 4 of my hands-on career companions. I will present you our work with this presentation, which will last more or less 15 minutes. So I worked with Daewon Kim and Song Hee Han from the Hydraulic and Environmental Lab, but also with Han Taek Shin and Seo Han from the Disaster and Water Management Lab. The main body of the work was to study the flow on 2 different areas. One along the Sungin River, which is a straight fitted stream, and the other one inside the Buol district. Both studies will present used models, results, and possible solutions. Water quality will also be approached in the case of the Sungin stream. We will start with the river flooding case. First of all, research area about the river flooding is Sungin stream, which starts from the Buol district to Nandong Reservoir. Discharge water from the Mansu sewage treatment plants flows and walking trails is on the both sides of the river. So we have presented the problems and solution to the stream through modeling. ECRAS and QGIS were used to model the Sungin stream. ECRAS is a program that models the hydraulics of water flows from natural rivers and other channels. After simulating by setting condition into ECRAS, we predicted the flow location and used QGIS to build a DEM and convert a cross-section to 2D to calculate a flow area in ECRAS. When we built the ECRAS model, we set a new manning factor by reflecting the real condition in the basic model. And after analyzing the results, we suggested to improve the levee height with flood prevention measures. We refilled this table when we decided the manning coefficient. We refer to Sungin stream's field photos when setting the manning coefficient. The water from upstream to Bangor Bridge is clear. The waterway is straight and the riverbed has vegetation, so the manning factor is set to 0.045. And the Bangor Bridge to Yeongsu Bridge has gravel and stone, so it is set to 0.05. Finally, from Yeongsu Bridge to the downstream, we used generic factor 0.03. As a result, we can see that there were more flood when we considered manning factor according to reality instead of manning factor according to basic model. So this part of calibration is very important. You should always keep in mind that reality always varies significantly from models. This figure shows the frequency of 100 years from the longitudinal cut. The pink and purple lines represent levees, which can be seen to be flooded between 3.3 and 6.1 kilometers downstream after 100 years return period. In particular, the left levee is lower than the right levee, so flooding is more expected to occur to the left. On the map, the left side of the river is a company complex, which is expected to cause a lot of damage when flooding. So this area needs flood prevention. We improved the levee height of the flooding area. Today, the frequency of torrential rain is increasing. So the criteria of river design is increasing also. Therefore, single stream or local stream was originally designed for 100 years plan, but the levee was raised with reference to the frequency of 200 years. So in addition, the Nile levee were also modified to keep the height of the levee constant, as well as to increase the aesthetical effect. That way, we can check there is no flood as a result of the resimulation. With the longitudinal cut, it is easy to see the changes in water level and the height of the levee immediately, but it is difficult to know the extent of flooding. Therefore, we try to express the flood with an aircraft mapper after building the DEM. This is the result we got. We can clearly see that the industrial complex area and the rural district will be safe according to the improvement of the levee that we made. Now some quick words about water quality. The picture on the left shows the upper part of the Saint district. The middle figure is water quality of Yansu and Donmac Bridge. As you can see, sometimes water quality doesn't reach the legal standards. According to Saint Stream report, we found a significant lack of dissolved oxygen. This report confirms the existence of stagnant zones in the middle stream, which leads to an increase of pollution as it runs downstream and the predisposition of dissolved oxygen to fall. So to improve water quality, we can apply a variety of methods like those ones, dealing with bed, artificial wetlands, or even purifying plants. However, these methods are determined by engineers in consideration of the situation and conditions in the applied area. And in this study area, in the second stream, we can expect positive effects by increasing the efficiency of the self-purification only if sufficient dissolved oxygen is maintained. Therefore, microbubble will be applied. So I would have loved to show you a microbubble simulation and how this technology works. Sadly, with this recorded PowerPoint, that's not possible. So I showed the link. I recommended you to do a screenshot, and you could search by yourself, of course, if you're curious. And if you don't have time, I will show the link again at the end of the presentation. So then we were thinking about where to install the microbubble generator. We think about stagnant water, which will be the best water quality in the riverbed. Therefore, to find the installation location, we ran the simulation with normal condition, and we found two sections where velocity is rapidly decreasing. As you can see, this area indicated bad water quality, so we're going to install a microbubble generator right there. Onga River in Japan is a good representative case of water quality improvement using a microbubble generator. Here is the location of Onga River, and microbubble generator was installed in 2004. The figure 3 represents the dissolved oxygen distribution according to installed or not in the river. Following the report, now they use the water as intake facility. So if we can install a microbubble generator in Sangi, we could expect improving water quality like this. So this is the end of the river flowing case, and now the next part will be the inland one. On July 2017, a significant rainfall event occurred in Guodong, Incheon. Rainfall gauges in the affected area recorded between 90 millimeters and 110 millimeters of rainfall over a 6-hour time period, and more than 100 area residents reported flooding. With the EPA stream software, we were able to recreate this event. You can identify the flooded area with the red zone. Then, why did the flooding happen in that place in Guo district? This is a question we asked ourselves. We analyzed it for two main reasons. The first is that the cross-sectional area of the channel is small compared to the order of the main channel. In order to identify the cause of inundation in the target area, we analyze the pipe connection relationship. A high order means a large amount of water is collected. Therefore, the higher the order is, the larger the size of the pipe has been. However, the pipes in the white box on the right figure are relatively small to handle the large amount of water transported upstream. The second reason is that the Bull district is located in the lowest places. According to the DEA that we made, the average elevation of the area where the actual flooding occurred was 8.3 meters, which is considered to be the lowest in the target area, considering that the average elevation of the nearby area is over 9 meters and over. Then how can we prevent the flooding in rural district? More than 71% of the total area cannot be developed. It means difficulties in expanding and new pipes networks. So we found two sites where we can build storage tanks. Those sites are parks located in the city and where it is easy to install an underground storage tank. So we applied a 65,000 ton storage tank. It was confirmed that no currents occurred in the main flooding hub. So of course, this is the capacity considering only storage. When draining facilities such as pumps and flood network are applied at the same time, the storage capacity will be significantly reduced. So it's not really 65,000 tons, it will be something lower. There are practical policies that can add credibility to our results. In fact, Namdonglu in Xi'an decided to build an underground storage tank equivalent to 50,000 tons, including the area where we build the reservoir. There are differences in storage capacity, but our results can be judged to be reasonable. So thank you for your attention. Thank you again to Professor Dongwu who will allow us to work on this project. And I hope you will enjoy to participate with your team as such as I did. Keep going up.
Thank you very much, Victor Bernie. This presentation is conducted by Hydro-Asia Program in 2021, and Victor Bernie is present their team of groups research about the river analysis and urban drainage system for the flood mitigation. Thank you very much. And the second presentation is from Alejandro Portela-Langa. 중에서 표현 좀.
네, 알겠습니다.
Can you hear me? Alejandro? Your voice is turned off now. Please turn on your microphone.
Okay, can you hear me now?
Yeah, it's good. Your voice is clear.
Okay.
Okay, I will introduce shortly for you.
Yeah.
The second presentation is the analysis of flood mitigation and river restoration in urban stream of Korea. The speaker is Alejandro Portela-Langa from the Polytechnic University of Catalonia.
Okay, so good morning, everyone. My name is Alejandro Botella-Langa from Universitat Politécnica de Catalunya in Spain, and today I will introduce the work that was done by the Yellow Team during the Hydro-Asia 2021. Our supervisor was Professor Dongwu Zhang from International University, whose advisors were so useful for our team. These are the contents of our work, in which we focus first on the flood mitigation and river restoration of the Seonggi stream basin in Incheon. And after that, the ecological restoration in terms of water quality. The yellow team was integrated by engineering students from 4 different universities: Kyute Park, Jungmin Lee, Hisu Chung from Incheon National University, Julson Froa from Polytech Nice, Sofia in France, Alejandro Botella-Langa, myself from Universitat Politécnica de Catalunya in Spain, and Min-Soo Kim from Chungbuk National University. Our research area is located in Incheon, Korea. Seonggi and some areas from Google-dong were selected as simulation zones. Seonggi starts at Subongsan Mountain in Gyeonghyun-dong and flows to the West Sea through the Namdong Reservoir in Donchung-dong. The extension of Seonggi is 10.47 kilometers and watershed area is 31.96 square kilometers. Google-dong is located in Namdong-gu, Incheon. The study area is 0.42 square kilometer, and the area has been flooded 3 times in 2010, 2011, and 2017. The purpose of the simulation was to find the location of flooding area with 100 years return period discharge and prevent flood by modifying the cross section. This is our input data for Hackerash model, which we simulated using steady flow conditions. This is the result of the Hackerash simulation model with 100-year return period discharge. After we ran the simulation, we noticed that 9 cross sections were flooded. Flood was observed to occur in the upper mid-stream part. This place is the middle part of Seonggi stream. As you can see, with the 100-year return period discharge, this industrial complex area can suffer from flood. And this is because the left levee is not high enough in this section. This place is upper part of Seonggi stream. Same as middle part, these places also can suffer from flood. On the left side of the stream, there is a parking lot. If this area is flooded, then we can expect a lot of damages. On the right side of the stream, there is a wasteland, so we don't need to take urgent action to protect this area. On this slide, it can be observed the simulations before and after modifying the cross-section for the mentioned area. To solve the flood hazard around the stream, we created a levee to protect the area, and this levee is less than 1 meter high. This is the longitudinal cut of Seonggi stream after our modification. And we noticed one area where water level was close to the levee, but it didn't overflow it. We changed the downstream boundary conditions from the high water level to low water level and simulated with 20-year return period and 200-year return period discharge. Result shows that changing downstream boundary conditions doesn't help to reduce flood at upstream area. Considering sea level rise, we simulated downstream boundary conditions with 4.6 meter. Most of left levee was flooded, so we advise to reinforce them to prevent flood in the future. We did the previous simulation with the Manning number of 0.03, but considering the actual morphology of Seonggi stream, this number should be around 0.04. It increases the water level during the flood, but constructing higher levees should tackle the issue. We conducted stream model for flooding simulation. Our simulation purposes were to find flooding area with 50-year return period and suggest a solution to prevent the flood and check the applicability of our solution. We used 50 years return period rainfall as an input data, and we set the boundary conditions like this. Taking on the upstream part an inflow discharge of 66 cubic meters per second, and at downstream water surface elevations of 5.73 meters. As a result of first simulation, which has no modification, there was 4 areas in which flooding occurred. As you can see, the 2 areas have severe flooding. So we checked the cross sections of these 2 areas first. And also area number 3 seems to be better if this is connected to each other. This is the cross section of 2 flooded areas. When we observe the cross section of area number 1, it seems that there was too much inflow from the upstream. And it seems that the cross section of area number 2 has too small flow area in the conduit. So we modified only the size of the pipes on the flooded area and made a connection in area number 3. This is a modified simulation result, and it seems better than before. There was no more flood in area number 1, and the flood discharge of area number 2 was decreased. But areas number 4 and areas number 2 and 4 were still flooded. So we installed a tank and a pump in area number 2. It could reduce the flood in this area, and also we could decrease the flood discharge of area number 4 by increasing the size of the pipe. This figure shows the decrease of the water level on area number 3 after this modification. About the water quality problems on the study area, we identified 2 main issues. For analyzing them, we had the data of the water quality from Johnson Bridge and Nogmak Bridge. On the right table, we can observe the Korean standards for water quality. In the upstream part, close to the Johnson Bridge, the water quality data, it indicated a high concentration of BOD and low concentration of DO. Both of them indicators of the level of pollution of the stream. On the other side, we can also observe a high concentration of TP, which can result in eutrophication problems. On this area, our suggestion is to increase the intensity of the water treatment plants for improving the pollution parameters, or even creating new ones if it needed, and also implementing bioretention systems on the stream. Basically, this is systems of plants and trees capable to absorb the nutrients as the phosphorus and the nitrogen that are the main reason of the eutrophication. For the downstream part, close to the Dongmei Bridge, some of these parameters were even worse, likely due to the presence of an industrial area that can cause illegal discharge to the stream. So for this area, we suggest making an analysis of the discharge of this area and its sewer network, and improve it if it's needed, and also implement penalties to the companies that don't respect the environmental regulations. On this slide, we can observe that some experiments on bioretention boxes that conducted under laboratory conditions indicate that this kind of methodology are useful for reducing the presence of nutrients in water and then improve the water quality. These were the solutions and results for the flood mitigation and river restoration of the Songhi Stream basin in Incheon and its ecological restoration. Thank you very much for your attention.
Question from floor or online participant? Any question? Okay. When I see your river analysis result in page 15 and 16, in the downstream of the elevation, downstream of the water depth is decreased very rapidly in the page 15. Yes, the 20 years with lower water elevation for the downstream condition, like maybe the right side of the picture. So, do you think it is in the real case? Do you think it is a match with the real water depth comparing with the simulation result?
Again, can you repeat the question, please? Because the audio is.
Yes. So in the right side picture, the 20
Yeah.
years with the raw water level, in the downstream water depth is lower compared with the left picture, and their water depth curve is very rapidly increased for the upstream direction. So, do you have any mind for their differences of the water depth? Why the water depth is decreased rapidly in the downstream part?
Yeah, it's in the downstream part because we were using the low water level in the downstream part, because in this area it is this reservoir in which the main gates were open, so we can decrease this boundary condition in the downstream part.
Okay, so I think so. The boundary condition of the water level affected to the upstream direction of their water depth. But when I think you need more some compare between the higher downstream water depth and some low water depth compared together, and some of the case some curious why the water depth is maybe the low water depth became effective to the upstream, but in this case their water depth increase is very rapid. So some of the some real case we need the consideration of that. So now the picture sometimes is very some fields is not make sense for the water depth flow. Okay, it is just only comment from my side. And thank you very much for your presentation. And I think you're now the Spain is the midnight, so Spain is the midnight. So thank you very much for participation from your country.
Yeah, thank you very much.
Okay, thank you. And now we move to next presentation. Next presentation, the title is the design of the single stream and core district for mitigation of the flood damage using the HMS and EPA3. The speaker is Ye Choi and Jiun Jang.
Good morning, we are presenters here and Leslie. Today we will talk about how can we prevent the flooding issue in St. Stream and Jewel District using HMS and EPA3. First, the introduction of single stream and rural district. This is the single stream. It flows from rural district to Mandong Reservoir, and the upstream part is covered, and the middle part was used for agricultural land, and the downstream part for the industrial complex. So the water quality has deteriorated due to the inflow of sewage from the Mandong industrial complex and a personal complex. But it is getting better. And recently, heavy rain flooded the Simpson Street area. This picture is for district. It's located in Mandong in Chad, and this poor district is vulnerable to flood damage because it's located near the Sintichan drainage basin, and the drainage capacity of the square pipe is insufficient. Now, in this part, we try to prevent flooding issue in single stream using HMS. Actually, single stream's design period years is considered 100 period years, but these days, sometimes there are flooding issues longer than 200 period years because of climate change. So we consider the 200 years for preventing flood issue or future. First, for preventing the flooding issue, we modify levee elevation. In this upper part of the stream, there are flooding issues on the right side. So as you can see, it's not that big flooding issue, so we just modified the levee elevation of our temple center and the street part of the stream. And here the middle of the stream crossing the issue on the west side. We will mention it. We consider the near upstream side because we want to change the bank area more widely if we can. But the left side is the industrial area. That means it's too hard to make the bank area more wider. So we just modify the levee elevation about 6 centimeters to 57 centimeters on the sixth part of the stream. And as the second method for preventing the flooding issue, we modify the riverbed and apply vegetation. In this part of near the summer bridge has flooding issue, so we thought that to modify the areas. As you can see the flooding area, their land use are like camping, vegetation, and agriculture area. But when you modify the land, residential site is really hard to do that. So we just modify the agricultural land and parking area. This picture is the way we modify the land. We change the slope and height of the riverbed, and also we apply the vegetation on the riverbed. It's just putting up on the net, place the big wood to stabilize. After that, we put branches that are gonna grow for the rejects. And to protect the inverse part of the bank, we put up feathers. It's like a brad technique. We put the bottom of the slope to counter the effect of the river that can be a problem to vegetarians to grow. As you can see the pictures, we changed the riverbank slope and heights like that. And finally, we can prevent a flooding issue. And when we apply the vegetation process, it has several benefits. First, we can protect the erosion, and it can increase biodiversity through new settlements. Also, we can decrease the low flow, and many value is increasing as you increase the vegetation of your area.
Now we use SWIM to simulate urban flooding in tour. You can see our target area and our sewer network in this picture. We apply the following boundary conditions, which are from a flood event happening on July 23, 2017. In our case, we modify the rainfall in the program, so we worked with two different return period and rain event duration. We need to define the flooding points to find out which part of the flood occurs the most. With 30 existing time and 50-year, 100-year return period, floods occurred in the similar junctions. Yellow points are happening a little flooding, and red boxes are a lot of flooding, so we have to sort them. In the case of 16-minute rain event duration, the volume of total flood was different, but flooding area was same. When comparing the four conditions, the inlet point occurred big flood. This tells us that the most important condition affecting our simulation was the inflow. Now we modify the sewer system to mitigate flood. First, we change the pipe size. Second and third, we use the low impact development. It is an approach to environmentally friendly land use development. Fourth is we insert a reservoir tank and a pump. The first point red box was very high flooding, so we changed the pipe size, and then we could prevent the flooding at the inlet area. Second is we use the rain barriers. It's like a rainwater tank. A rainwater tank is a water tank used to collect and store rainwater rainfall. Third is we use the permeable pavement. By using that pavement, we can reduce runoff volume by trapping and slowly releasing precipitation into the ground. The red box is where the park is, and that point had a lot of flood, so we can install the underground reservoir. The area is 1,000 square meters, and the depth is 8.5 meters. By using this method, we was able to use the maximum of total flood volume by an average of 88%, and the sum of the total flood volume by 97%. Thank you for listening.
Thank you for the presentation. This presentation is played by a video presentation. So if you have any question, I will inform to the speakers. So is there any question from the floor? Okay. Thank you very much. And the next presentation is the development of the hydrological model in a waste small catchment using DHI microcurve. The presenter is the Kyuteba from International University.
Good morning, everyone. I'm Kyuteba from International University. My research title is hydrological analysis of an engaged small catchment using DHI math models. And this is my contents. First, I will explain about the research backgrounds and objectives. Second, description of study area. Third, methodology, and fourth, results, and for the last, conclusions. According to the water research, the number of extreme rainfall is increased all over the world between 1964 and 2013 because of human activities, and the international database said that the catchment is suffering from floods in 1994, 2000, 2011, and 2015, 2019. And this is the visually Martin flood damage status in 2020 October event. And there are still many small catchments that are not hydrological measured in catchment. And typically, the St. Louis Valley area, it has not been hydrologically analyzed. In this study, calibrated return periods precipitation based on November 2000 Nice airport precipitation event were applied to MIC model for estimate the outlet discharge and runoff coefficient. This figure 3 shows the location of our catchment. It located in southeast part of France, and our catchment is divided into 5 big sub-catchments, and the upper bar and external Desvik Kinin lower bar. The catchment area is about 2,800 square kilometers. Longest flow path is 114 kilometers. Figure 4 is target area, which is St. Blaise Valley, and it is in lower bar. About the geographical information of St. Louis Valley, the area is around 17 square kilometers, and catchment length is around 30 kilometers. Average slope is 23 degrees, and longest flow path is 12 kilometers. There are 3 rainfall stations near the St. Louis Valley area. Figure 5 shows the location of rainfall station for Levens and Carlos. collection of precipitation data began from 2020, and this is the reason why we used this airport precipitation for estimate discharge and runoff coefficient. And because this airport began to data collect from 1891, and table 2 shows monthly average precipitation at each rainfall stations. And this is steps of study. Calculating the runoff in mountain area is one of the most complex hydrological process because we have to consider 4 main controlling factors. The first is digital elevation model, second is climate, and third is land use, fourth is soil characteristics. Different combination of these 4 different factors determine complex runoff in mountain area. Most of input data for machines such as model domain and topography, land use, soil type should be prepared in ArcGIS. And this figure shows the process of ArcGIS. And DHI, MAXI, and Mike11 were used for hydrological analysis. The Mike model is from Denmark, DHI company, and it is an integrated hydrological model. In this study, we did coupling process to consider not only surface flow, but also channel flow. And this model comprises the finite difference and partial differential equation of mass and energy balance. This is my sheet module that we used, that we have to set in the model, and this table shows the required data at each module. As a requirement data of my sheet, we need topography and land use. The 5-meter DEM topography data is provided from this city hall, and to reduce the calculation time, we converted it to 10-meter resolution from 5-meter, and the observed elevation is 85 meter to 1,400 meter. And the land use data is also from this city hall, and the original data was divided into 788, but we reclassified it to 9 land use categories. After we reclassified it, the residential area is around 11%, and 89% is forest or agriculture. The particular values based on land use were adopted from previous research Chiangma, and such as leaf area index and rooting depth, crop coefficients. Data are from the Sophia Antipolis Laboratory. And soil type data is from US Department of Agriculture. The original data was consist of silt and clay loam, silty clay loam, but through the field investigation, we found that the down part of St. Blaise Vallon is consist of pudang, which is almost same with the sand. So we modified the soil type. And in worksheet, we have to set the hydraulic properties for the individual soil type. So we adopted from previous research Chiangma data for the input. And the precipitation data were provided from the Sophia Antipolis Laboratory, and simulation were conducted according to 6 different return period precipitation. This is the river network and cross section in the model. In saturated zone model, we divided into two regions because the down part of St. Blaise Vallon area cell type is Pudeng. And so if you see the blue color area, we set the lower level and initial potential head as -2 meter, and the orange color area is set as -1 meter. So as a result of this setting, the blue color area will absorb more water. So if you see the results of rainfall at the beginning, we cannot observe the water flow at Puding area, but after 26 hours from the rainfall, we can observe a little bit water in the stream, and at November 1st, 4 p.m., we can see the all water flow in the stream. This is the result according to the various return period precipitation. So if we apply the 162-year return period precipitation in the model in St. Blaise Vallon area, the observed peak discharge will be around 30 cubic meters per second, and runoff coefficient will be around 0.673. So this is the conclusion. First, YC model has been set up according to various return period precipitation, DEM, land use, soil type in St. Blaise Vallon area. And if the maximum return period occurs in St. Blaise Vallon, then the hourly peak discharge and runoff coefficient will be around 30 cubic meters per second and 0.673. And with this peak discharge, it is expected that the flood mapping for St. Blaise Vallon will be possible in the future study. And if necessary, it would be possible to redesign the downstream of St. Blaise Vallon based on results of outlet peak discharge to prevent upcoming flooding in the future. Thank you.
Thank you very much for that presentation. Do you have any questions from the floor? Okay. About the some small engaged catchment and their flow graph, flow discharge is very difficult to estimate to the explanation. So I got nice presentation and nice research. And in your research, you applied the 162 return period for flood simulation. So is there any possibility to more the flood condition to this your study area?
Because this region is only unmeasured region, so the maximum 162-year return period is the maximum return period precipitation. So I think 30 cubic meters per second per hour is the maximum discharge.
Okay, so some general condition, maybe it's the flow discharge is lower than 162 frequency years. So it is good the result for various return period and their flow discharge. So we can maybe apply to real area. Thank you. Thank you very much. And next is the Song Yang from International University. She will present the hydroelectric energy for flood mitigation in mountain small catchment using micro trainer network.
Hello, I'm Suni An in International University. My research topic is hydraulic analysis for flood mitigation in engaged small catchments using microneedle. This is contents of this presentation. First, I will explain background and objectives. Climate change is occurring around the world because of human activities and urbanization. This has resulted in increasing flash flood and torrential rainfall. The location of flooding has significant impact on the scale of damage, especially in mountainous area can get the big damage because of steep slope and high water velocity. And in addition, lots of road in mountainous area can get the big damage because of the sediment transportation. Most flood prevention and flood resilience mapping are active only in urban areas with high population and sufficient infrastructure, but in mountainous area, flood damage research are insufficient. So this study conducted a hydraulic analysis of mountainous area. This is the Bar catchment. Bar River is in south part of France. The Bar catchment is divided into 5 big sub-catchments: Upper Bar, Tigny, Elson, Vesuvie, and Lower Bar. Recently in Bar catchment, frequency of torrential rainfall has increased recently. Last year, big flood occurred in Saint-Martin-Vesuvie region. At that time, the precipitation was 500.2 millimeters in 24 hours. And Lower Bar has also big flood damage experienced before. The Lower Bar subcatchment is in the bottom of the other 4 subcatchments, so all tributary of Bar River flows to this catchment. The Saint-Blaise Vallon stream is also one of the tributary in Lower Bar, where a small town is distributed, although it's mountainous. It could happen not only mountain flood like landslide, but also human casualties and economic losses. Therefore, in this study, Saint-Blaise Vallon was determined as a study area to predict flood damage. There are 5 bridges in bottom of Saint-Blaise Vallon stream, but bridge is not available in my model, so all bridges are set as culvert. This table shows the specification of the culvert, so this value was set in my 21. This page shows the satellite view of culverts and cross-section. Buildings are distributed along the stream and river. This means that if flood occurs, residential facility can get the big damage. In this study, discharge of 50, 75, 100, and 162 year return period were used. The reason why 162 year return period were used is it made really big flood damage to Nice Airport and Lower Bar in 2000. First and second peak value are the result of the random amount of precipitation by previous research team to calculate the outflow after 100% saturate of the land. So 24 hours of discharge, including the third peak value, was used for the simulation. Mesh was generated by ArcGIS and BikeMesh generator. The minimum angle of the mesh should not be less than 10 degrees, and since the DM used in the study was 1 meter grid, so smaller mesh than 1 meter is not necessary. They make simulation too long. So like this figure, it was combined into one. In this way, total 11 buildings were combined. The mesh type and maximum area are divided by 5. The mesh type of St. Blaise balloon stream are quadrangular and triangular. The direction of stream is almost constant from high elevation to low elevation, and there is really few flow of transversal direction. Therefore, using the mesh type of stream as a quadrangular is more efficient for simulation. The mesh type in all other are set to triangular types, which are more accurate than triangular mesh. In addition, the mesh size set differently depending on the importance of fluid analysis. Structure curvature 1 and 2 is big enough to be long curvature. DM of long curvature should be modified because the model setup requires the elevation of the structure. Boundary condition was set like this. After that, simulation was run. These figures are flood maps of 50-year return period. It shows that a flood occurred on the right side of the curved side. Some of the residential facilities were flooded. After half an hour of peak time, the overflowing water flows into the lower land and flooded other residential facilities. These figures are 75 flood map of 75-year return period. Flooding begins at the same point as the 50-year return period, but more areas are flooded. There is a flood on the left side of the curved 4, but it's mountainous area with no residential facility. These figures are flood map of a 100-year return period. The right side of the curved 5 flood is gradually wider, and this flooded water joined stream near curved 3, and a new flood occurred near left side of curved 3. It caused water flows to downstream and road flooded. Finally, these figures show a flood map at 162-year return period. Before peak time, all area along stream were flooded. 23 of 27 residential facilities were flooded. Although peak time is 11 a.m., but at noon, the flooded area was the largest. Hydraulic analysis was conducted on 4 return period precipitation, and from 50-year return period, flood was observed. A common conclusion about flood analysis is that the all flood begins near curvature. This can be suspected that curvature capacity was less than flood discharge. Therefore, increasing the capacity of culverts can make reduction of flood. Second, the result of the flood zone calculation shows that the most flooding does not occur during peak time with the highest discharge. And the flooding area is flooded for a long time after peak time. This means that even if precipitation is reduced or stopped, damage can still be serious. Third, 23 of 27 residential facilities distributed along the St. Blaise Balong stream were flooded at more than 100-year return period. This means that flooding damage in this area is severe. Even small river needs to be enhanced by standards of river design. If the infiltration characteristic of this area and precipitation data is accumulated, we can improve the analysis results. In the future, it's expected the improving the flood model in mountainous area through experience and formulas through various hydraulic models. Thank you.
Thank you very much for nice presentation. Do you have any questions from the floor? Okay, and it's very interesting research for real area for engaged small catchment, and based on your simulation results, we can see some details about some flooded area. And when you consideration about the flood depth, where is the more some critical area for the in your target district?
Upstream of this stream is can get a big damage because left side of the stream is has lots of residential facilities, so it can get the big damage. And road also, all roads were flooded, so road also can get the big damage.
Okay, and in the picture, the graphical view is very fine resolution. So I think it can apply to our real area. And if you suggest if you increase the more accuracy about the model for application of the real district, could you suggestion for the improvement of your research?
I think improving here can make more accurate level.
Okay, good. Thank you very much.
Thank you.
Okay, now we have the 5 presentations about the Korea-EU Educational Cooperation Program in Asia. Some of the presentation is conducted by play the video, so I'm very sorry to some communication with the presenter, but this is very nice presentation and it's good for research. So we hope that these research outcomes can apply to in Asia and the world, and for improving the estimation of the flood. Thank you very much for all participants, and now I want to close our session, and after from 10 and 25 we will continue the Korea-EU education presentation. Thank you very much, everyone.